everyone. Welcome to my talk. Let's say I think compared to other low-level programming technologies, currently we are focusing on the application layer in this talk. So I would like to discuss about how we secure Web3 use cases with Rust and OPTE. So before we start, we can have a basic understanding of how Web3 works. So basically, Web3 is built on top of the blockchain. So the blockchain serves as kind of decentralized infrastructure to host applications. The applications are written in smart contract. And the user to interact with the smart contract by issuing and signing transactions. So the transactions here is like describe the user intent. For example, to transfer crypto tokens or calling smart contract functions. But how the user is identified in Web3? So it's basically related with key pairs. There's no username or password. Each user maintains a set of asymmetric key pairs, and the public key serves as their on-chain identity, which is also called on-chain address. And the private key is manage the security by themselves and to sign transactions. So following this like basic setup, so we have our first use case, which is called self-custody wallet. So basically, the wallet is kind of a utility for the user to manage their Web3 credentials and assets. Typically, a wallet might help the user to generate multiple key pairs, but all those key pairs are derived in a deterministic way based on root secret, which we call entropy, right? You can see in the left figure, so the wallet when the wallet is first created, it will display the those root of trust root entropys in human readable words, and users might take paper and write them down to physically back up them in a security place. It's a very ancient but effective way to back up their crypto wallet. So every time, so if you have the mnemonic, you can back up your wallet across devices, either in your mobile application or a browser extension. So in the self-custody wallet, the main threat is to leaking the private key or the mnemonic. So the security requirement here is that we need a way to protect the confidentiality of the mnemonic or the credentials across their entire lifecycle. Not only the creation in use, but also at rest. And also, we need for the user to access those credentials, the context should be confirmed by the user, and also the transaction's integrity also has to be preserved. Another use case is about the decentralized physical infrastructure network we call DePIN. It's developed based on the traditional IoT environment. Basically, in traditional IoT, we purchase a device and we use it. That's it. But in Web3, they call it some kind of smart IoT device. You bought the device, you will get reward of crypto tokens, and you share the use of the device. Maybe, for example, you share your bandwidth, you share your storage, then you will also get rewarded by crypto tokens when you're using those IoT devices. So the rewards are based on verifiable contributions to the network. So here, there are two types of key threats. First is that fake devices. What if I don't own the device, but I claim I have one in order to get the reward? And also, even if the device owner might has the potential to do evil, right? Like to issue false claims, like pretending to provide services they don't actually deliver. So the security requirements here that in addition to the credential confidentiality, it needs device authenticity and also the proof of utility. So TrustZone makes, I think, is a perfect solutions, a technology to provide strong security for Web3 in those cases, especially when we have the ability to build trust applications. I think a very good example is about Samsung. Samsung have their own blockchain wallets built in with their phones. They are leveraging, I think, Qualcomm TrustZone to provide all the Web3 functionalities to manage, help users to manage their crypto assets. And also they also provide a trusted UI for the user, like to confirm transactions. But in terms of TA development, I think there are some unique requirements in the Web3 world. So first is that crypto blockchain crypto algorithm has some unique crypto primitive requirements. So these crypto, for example, the SEC P256K1 is not available in existing key star, meaning that we cannot reuse the existing well-defined key star functionalities. And also we need to attend implement a lot of Web3 related logics in the trust application, like transaction parsing, like mnemonic handling, and also like transaction detail, the confirmation kind of stuff. And also in the DePIN case, we need the flexible attestation capabilities. We can definitely implement this in each existing TAs in C, but it faces memory risks, and also they are very limited primitive to use because today's Web3 is mainly built on top of Golang and Rust without any legacy burdens. So this is where our project Teaclave TrustZone SDK comes to play, and the Teaclave project is incubating and in the Apache Foundation. The original goal is we would like to enable enabling trust application development using Rust. The thing we do is basically we provide Rust APIs bridging to existing OPT primitives to let TA developers implementing their logic purely in Rust. And also currently we have two modes. So for default we have no STD, which means that it's very lightweight bindings for legacy TAs that requires very limited primitives. And also we in the Rust community we implement the target STD target specified for OPTE. Then we have more ability to support to have let the TA developers to have the Rust STD support, which can be enabled much more complex use cases. So over the years, we also collaborate with the OP community, to align for example, to align the release schedule, kind of stuff. And the benefit of developing TAs in Rust is very obvious. For example, the developer no longer to worry about memory safety issues. I think even today, the main concern or security concerns in the trust applications is still memory safety, right? And also, Rust itself provides very powerful type system, and also provides zero abstractions, the comparable overhead as development in C. And also, all the checks are enforced at compile time. And also, by enabling Rust SDK, we have a lot of Rust craze to use out of the box. For example, developer can use 3D to serialize and deserialize the parameters or the TA requests in a very safe manner. And also, they have vector hash map. Also, we in the Rust community, we have the RIN, which acts as the crypto craze, and also have the TRS available. So by providing this SDK, I think we would like to in addition to providing the SDK, we also like write sample TAs to demonstrate how efficiently we can use the SDK to solve the real world problems. Here is an example for the wallet for Ethereum. You can see that we from the dependency like a manifest, we can use most of the existing Rust craze in the Web3 world without any change. And I think it's only a few hundred lines to implement a wallet for the Ethereum use case. But for the DePIN use case, I think let's recap. So I think we need the device authenticity and the proof utility, right? So obviously, TA attestation is the ideal solutions to solve these, like to achieve these two security requirements. But here our trade-off is that, so how should we provide like such a unified interface for our trust application developers who use Rust, right? So I think today there's a lot of like low-level primitives provided by OT system. So, but how should this be in the user space? So we are working on something like this. So we provide attestation abstraction, like for ER SDK for all the TA developers. So we isolate all the attestation-related logic into a dedicated TA we call coding TA. So in the coding TA, we abstract like three entities. The first is the coder, which provided a unified interface for all the existing application TAs. The TAs can use a very standard, simple interface like init to get connection with the coding TA and like to invoke only get code with context-aware data to get a verifiable code. Inside of the coding TA, we have the attester abstraction, which adopt to the existing primitives available in the OPT OS. And also we have a part of endorser abstraction that aiming to deal with the like vendor-specific secret provisioning. And here, if we look at this example, we have the attester like dealing with the attestation, and it maintains a attestation key. And also, the endorser can have access or direct access to a device key, right? We can use the endorser to endorse the attestation key held by the attester. Then, for a DePIN vendor, when they manufacturing the device, they can issue like a device certificate for this provisioned device key. So after that, a remote party can verify the code through or can verify the entire trust chain routed from a vendor PK, and which verifies the device key, and the device key endorses the attestation key, and that's the authenticity of the attestation report is verified, and you can check the measurements inside the report. That's the basic idea. So in our currently prototype implementation, like we adapted our attester abstraction to the existing attestation PTA in OPT OS. And you can see that there are existing measurement primitive available in the OPT OS, and but here we are doing a slight patch about to enable the authentication. Like we want that only our coding TA is able to access those primitives. It can be treated as serving the coding TA as a user space guard for the existing OS primitives. And also for the endorser part, we integrate with the vendor specific PTA. So we are using NXP like a board for development. So we have we notice that there are manufacturing protection functionality like perfectly like solves the secret provisioning problem. So it originally it would like to provide a security manufacturing process, like to provision root security to the board, and also the OEM vendor can maintains a trusted public key list of all the provisioned secrets. We, in our use case, we will the root secret is securely stored in the hardware secure module inside IMX called CAM, and also it requires secure boot to be enabled. So in our case, we will treat this kind of secret as the device key. And in existing OP OS, there's a PTA handling and providing like assigning and get public key interfaces to indirectly access the device key. So we are using the endorser to to talk with this PTA and let it to endorse our attestation key. So I would like to emphasize that with this flexible abstraction, in the future, if we have other vendor-specific PTs available, we can easily being adopted to the coding TA's design, and without the application TAs will automatically benefit from the underlying change. So here is our attestation. Here is our attestation abstraction recap. So we provide a very flexible and modular abstractions for the TAs to using attestation functionalities, and we isolated all the attestation stuff into a dedicated user space TA, and it can be easily adopted to any future changes or future future available primitives provided by the OPT OS. And also we also in such way we also leave the we will also did not consume too much resource by the TA because by the application by trust applications, because we are providing this as a dedicated TA, not as a dependent library implemented in the targeted existing trusted applications. So here is a brief summary of today's talk. So first we have a basic understanding of all the Web3 use cases about self-custody and also the DePIN use cases. And we abstract how TrustZone can help to ensure the security of credential confidentiality and the device authenticity, and also the verifiable service claims. And also we introduced a secure and flexible TA attestation framework, or dedicated coding TA built with our Teaclave Rust TrustZone SDK to leveraging and extending the existing OPTE primitives. I think we have done the prototype and we will release soon. Stay tuned. That's almost about my talk. I'm ready to take questions.
So can you clarify the protocol between the relying party and the attester?
Okay. In our previous experience in SGX, we are trying to uh, bridging the testing report in the TLS protocol. So we are using TLS and embedding the verifiable attestation report into the certificate verification phase, and in this way, a remote party can directly talk with our coding directly talk with our trusted applications to establish a mutual verified channel.
Sorry, you mentioned some protocol. Which protocol? Are you mentioning Intel's RATLS protocol?
Not Intel's RTLs, but I think Intel has a paper
Yeah.
how to embed the remote attestation report into the TLS communication. So basically, the attestation is based on the established mutual attestation channel leveraging TLS protocol.
Right, but maybe to be very specific.
Hmm.
So my question is, how is your protocol different from Intel's RATLS protocol?
We don't differ. We don't difference from the RTLS protocol.
So your protocol is not different from that. So that's the
Yeah,
same.
yeah,
Okay,
yeah,
okay,
yeah.
okay. So
So here you can see that we didn't show the protocol part because for the protocol we are leveraging the Rust TLS to use to establish a trusted TLS channel. During the channel establishment phase, like we present this variable report. Yeah, I think logically it is still the same with the RATRS from Intel.
okay, so one quick question that I will also ask is in your protocol the signing that's done by the attestation key, is it happening before the TLS protocol handshake starts?
Yes.
Okay, okay, thanks.
Yes. So here we just present a way that how we get the attestation, verifiable attestation report. We did not mention about the protocol part. Yeah, because I think no matter what protocol it is, at least we need something that we need a way to let the trusted applications to get the verifiable attestation report, right?
Yeah, but there
Yeah.
is a problem in that protocol that you can namely have the replay attacks. So you generated an evidence,
Hmm.
you use it in every session that will be run by that attester.
No, I think it depends on how you use the protocol. Here, you've seen that uh, if you use it in an unsafe manner, it is unsafe. But here you see that for get code, we have a user data part, right? Here,
Yeah.
also the user data will show in the testing report, which is similar as the SGX report does. So conceptually, if you the preferred way to use the RATLS protocol is that you generate a key pair, and then you embed that public key into the user data part.
Right, but we did an analysis with exactly that you are mentioning.
Hmm.
So we generate a key pair, we put it inside the
Hmm.
that's what Intel calls as R data,
Hmm.
and it still cannot avoid the replay attack because this field will be the same for all sessions that it will run, and I don't see how this will provide
Uh,
protection against replay
yeah,
attacks.
but I'm not sure how you define the replay. So
So I would
we are
define
maintaining
maybe
the a genuine so the ideal use case is you establish a new session every time you want to talk to a trusted application, right? You have to establish a new session.
oh, so
Yeah,
every time you
you
establish a new connection to
yeah, yeah,
okay.
yeah. I think that's the way how the RETLS is designed, right? So it's the I think the granularity is doing on the TLS session base, right? So you establish session, you attest the remote party is trusted, then you can reuse the session to talk to it. I think secure property is protected by TLS, right?
Okay, then
Yeah,
I will talk
yeah,
to you
yeah.
afterwards. Thanks.
Okay, thank you.